made by Toyota colleagues. After we'll have a break, half an hour break, maybe longer since we are ahead. And then we'll have 3 additional presentations until the lunch break at 12:30. Okay? So for the first part, let me welcome Hideki Goto from Toyota Corporation. So Goto-san worked more than 20 years and is the chairperson of the JASPAR Next Generation High-Speed Network Working Group. He has been contributing to the standardization of automotive networks such as FlexRay, Bluetooth, and Ethernet at JASPAR, and is also a steering committee member of AutoSAR and a board member of Open Alliance, actively participating in standardization of the automotive industry. And Yuki Wakida, who has more than 16 years of experience in ECU software development at an automotive ECU supplier. He joined Toyota in 2021, and since 2025, he has been engaged in the advanced development of in-vehicle Ethernet technologies, focusing particularly on applying 10BASE-T1S to next-generation automotive network architecture. So I'll let you introduce your topic, and which is a feasibility study of scalable in-vehicle network development using 10BASE-T1S, a performance-based stepwise migration approach for CAN and CAN-FD.
Thank you for the introduction. I'm Hideki Goto from Toyota, and my colleague Yuki Wakida will present as feasibility study of 10BASE-T1S. In this study, we have been evaluating the feasibility of adapting 10BASE-T1S as a replacement for CAN and CAN-FD communications. At first, let me introduce the photo. The photo shows Toyota's urban city, which is a futuristic prototype city near to Mount Fuji. You can see Mount Fuji. And it's designed as a living laboratory for testing advanced technologies like autonomous driving, robotics, and smart homes. It aims to create a sustainable, connected community where people, building, and vehicles go together, work in harmony. That city serves as a future model style. However, I've never been to there, so I'm not sure in detail. Okay, here is today's agenda. I'll start with a brief introduction, and we'll explain the proposal for 10BASE-T1S, migration to 10BASE-T1S. Then I will hand over to Yuki Wakida. He will explain evaluation analysis. Okay, our vision is clear: scalable and sustainable E architecture. So, why is this important? Because we need a full-line strategy to meet the diverse needs of customers worldwide. Scalability and sustainability are important. Creating an architecture that works for both high-end and low-end models. That is a big challenge for us. But we are taking an evolutionary approach and making the most of Ethernet's strengths. This is how we deliver a global solution for every vehicle in our lineup. Let's talk about the CAN and CAN-FD communication. CAN and CAN-FD remain backbone of real-time and signal-based communication in vehicles. And they dominate because the ecosystem is established, well established, and making replacement difficult. Currently, we are using widely in both backbone and edge communication. Let's look at the numbers. Overall, we have 18 buses per vehicle, over 1,100 frames, and nearly 25,000 data bytes. To secure enough bandwidth of backbone, we need to use multiple buses. This shows how critical CAN and CAN-FD remain in our architecture. Okay, let's move on to key point of our migration proposal. I will explain why this migration is important and what benefits it brings. Let's look at the migration concept. Our goal is to keep the same backbone communication frames and data volume, but replace 2 CAN-FD buses with just one 10BASE-T1S. Why is 10BASE-T1S? Because alternatives 100 and 1000 BASE-T1 require switches, which significantly increase cost. Sorry to switch vendors. This approach simplifies the architecture and reduces cost. Look at the picture. So now our current uses CAN-FD for 2 buses, and we can achieve the same performance using 10BASE-T1S with multi-drop communication. Okay. Let's look at the CAN latency constraint. Our CAN requires latency to be less than or equal 20% of the cycle period, which is controlled by bus load calculation. The number of 20% comes from our application constraint point of view. In the case of 10 millisecond cycle, that means the CAN latency constraint, the CAN latency must be 2 milliseconds or less. This 2 milliseconds is our key constraint for migration. Left side, you can see the left side. So how arbitration and message scheduling work across multiple nodes. It is a window, latency window is clearly limited to 20% of big periods. And the right side, the data size, this is the data size. Data size shows from the multiple ECUs across the consecutive message, consecutive transmission periods. So that this indicates that the minimum cycle period, period cycle is 10 milliseconds. So the can baseline latency requirement for migration within 2 milliseconds. This is key point. Okay. So why the PLCA cycle duration is variable? As you know, PLCA is very variable. Depends on the schedule. So it depends. It depends on three factors, main three factors. The number of nodes, the frame length per node, and the number of burst transmission per node, meaning consecutive message. This diagram shows two scenarios. One is normal mode. The other is burst mode. In normal mode, PLCA cycle is relatively stable. But in burst mode, consecutive message can significantly extend the cycle time. So PLCA cycle meet 2 milliseconds constraint, latency constraint. Okay. This slide shows how we configure PLC to keep the cycle time within 2 milliseconds. So at first, we assume a certain number of nodes. So one is coordinator, three nodes, three follower nodes. It comes from our architecture. Then, next, the application data length per frame is set between 8 and 64 bytes due to CAN and CAN-FD payloads. Finally, burst count is calculated automatically so that PLCA cycle stays under 2 milliseconds limit. You can see the diagram. The maximum PLCA cycle would be 1.69 milliseconds, which satisfies the latency requirement of 2 milliseconds. This configuration meets our performance, same performance based on CAN communication. So we can use same performance at the 10BASE-T1S. Okay. This slide shows the key benefits of our migration approach. The condition is that 2 milliseconds. The condition is that the PLCA cycle remains 2 milliseconds, and the frame count stays unchanged. So this means one 10BASE-T1S provides more than 2.2 times the bandwidth of CAN-FD. So this approach simplifies our architecture and reduces the cost. Thank you. I will hand over to Yuki Wakida.
Thank you. Wait a moment, I use magical iPad, sorry. Now I will take over from here. In this section, I will present the communication performance evaluation results based on the PLC cycle configuration introduced earlier. In this evaluation, 2 CAN-equity backbone buses were replaced with a single 10BASE-T1S multi-drop bus. We verified whether this configuration can meet real-time communication requirements. First, let me explain the software evaluation environment. The test system consists 4 nodes. For the hardware, each node uses RH850 U2A 16 and LAN 8651 Mach5 device. The CPU clock was set to 400 MHz, and the SPI interface operated at 20 MHz. For the software, we adapt the AutoZar Classic platform and implemented standard modules such as COM, PD router, socket adapter, TCP, Ethernet interface, Ether driver, Ether transceiver. Next, this slide shows the measurement results of the PLC cycle. The condition was that all nodes transmitted 4 frames of 64-byte application data within the same cycle. I've shown the graph. I've shown the graph. The theoretical PLC cycle was 1.69 milliseconds. And the measured value, include file latency, was 1.72 milliseconds. Both are within the 2 milliseconds requirement defined the CAN communication, confirming that the latency requirement can be fully satisfied. Next, let's look up at the latency measurement results. The graph, 2 graphs, compares the frame latency ratio across transmission cycles. In the left here, measured under actual vehicle traffic condition, all frames stayed within 20% of the cycle time, which means the latency requirement 2 milliseconds for the shortest 10 millisecond cycle was fully satisfied. However, let's look right graph. However, as we gradually increase the number of transmitted frames, we observed that when the loaded increased by about 18%, some frames shorted to exceed the 20% latency limit. This is now let me explain the reason for the latency increase. The Mach5 used in this evaluation has only one TX54, transmit FIFO channel. When short period and long period frames are queued in the same FIFO, their transmission order can cause blocking. As shown on the left, if a short period frame is at the front of the queue, it can be sent immediately in the next PLC cycle, achieving low latency. But as shown on the right, if the short period frame is behind longest period ones, it must wait until the long frame is transmitted. This results in head-of-line blocking, and some frames fail to meet the latency requirement. Using a file with multiple transmit buffers is expected to mitigate this blocking issue. Finally, let's look at the start time comparison. And finally, this shows the time from reset to release to the transmit of the first frame. For CAN-FD, the measured startup time was approximately 55 milliseconds. And for 10BASE-T1S, about 61 milliseconds, difference of only 6 milliseconds. This means that 10BASE-T1S achieves almost the same startup performance as CAN or CAN-FD. And the impact on implementation is negligible. Now, let's move on to the next part, MC resources analysis. In this section, I will explain how the adoption of 10BASE-T1S affects MC resources, such as ROM, RAM, and processing time, and also share the evaluation results of several optimization approaches. First, let's look at the MC resource footprint by comparing 10BASE-T1S with CAN-FD. The graph on the left shows comparison results of resource usage between the two protocols, 10BASE-T1S and CAN-FD. And the graph on the right shows the ratio of 10BASE-T1S usage to the total MC resources. As shown, ROM and RAM usage increased to about 4 times that of CAN-FD, respectively. However, when viewed against the total MCU capacity, this increase is relatively small and remains within a practical range for implementation. On the other hand, the processing time increased to about 2.5 times that of CAN-FD. Although this increase is smaller from ROM or RAM, it still accounts for more than 30% over 10 millisecond task, which makes it a key concern for system designer. Therefore, reducing CPU load becomes an important consideration. As shown in the previous slide, processing load becomes a concern when adapting 10BASE-T1S. To address this issue, we evaluated the impact of adopting the OSMP architecture. The graph below shows the evaluation results. Please note that the MCU used in the study doesn't support OSMP. So part of the OSMP data was estimated based on measurements from on OSMP capable MCU, U2C. As a result, we observed a significant reduction in RAM usage, while ROM size and processing time showed only minor improvements. Overall, OSMP demonstrated better MCU resource efficiency than the conventional MAC-PHY approach. Therefore, OSMP can be considered a promising option for implementing 10BASE-T1S in automotive systems. Since the processing time issue was not fully resolved with the OSMP approach, we explored another option, L2 direct communication. In this method, the upper layer of the Ether stack, such as socket adapter and TCP, are bypassed. And communication is performed directly at layer 2, the data link layer. The graph below shows the evaluation results. Please note that the CDD part includes estimated value, so the results should be interpreted as approximately comparisons. With this approach, we observed that the overall MCU resource footprint, including processing time, become much closer to that of CAN-FD. Although the method limits the flexibility of upper layer protocols, such as SumIP, it is considered a highly effective solution for reasonable replacing CAN-FD communication while maintaining real-time performance. In the final part of the presentation, I will summarize our key findings and share our outlook for future development. In this study, we evaluated the performance feasibility of migration from CAN and CAN-FD to 10BASE-T1S using the same frame structure and data that are actually used in production vehicles. As a result, we confirmed that a single 10BASE-T1S bus can replace more than 2 CAN-FD buses, while maintaining latency within 20% of the communication cycle for all frames, meeting the real-time performance requirement defined by CAN. We also found the startup time of 10BASE-T1S is almost identical to CAN, showing minimal implementation impact. And regarding MCU resources, ROM and RAM usage are within acceptable ranges, although increase in processing time remains a point for further optimization. As our next step, we plan to evaluate 5 devices with multiple transmit buffers to mitigate head-of-line blocking and to optimize processing load by introducing layer 2 direct communication. Based on the finding of this study, we aim for a pragmatic and stepwise development. Instead of replacing of existing networks with 10BASE-T1S at once, we plan to introduce its selectivity in area where it brings the most benefit and efficiency. This approach enables smooth migration, allowing coexisting and mutual complementary with existing CAN and CAN-FD systems. To realize the vision, we will continue our study on unifying multiple CAN-FD backbone within the system. In parallel, we plan to explore the use of RCP, the internal use case evaluations, while participating in ongoing discussions within the Open Alliance GC18. That concludes our presentation. To recap, we demonstrated that 10BASE-T1S can serve as a scalable and practical migration path from existing CAN and CAN-FD systems, while maintaining real-time performance and implementation feasibility. Thank you very much for your attention. We look forward to your question and discussion.
Thank you, Wakida-san. Thank you, Goto-san. If you can come on stage maybe for questions. Since we are out of time, 20 minutes of questions if you want.
Okay.
Okay. José.
Okay, thank you very much for your presentation. I have one question. State of the art in the industry for bus load usage CAN is around 50%. So I have one question. To achieve your latency objective of 2 milliseconds in CAN-FD and in 10BASE-T1S, which is the estimation of bus load usage? How high is your bus load usage?
Thank you for the question. So actually, we are using 60% of CAN-FD bus load based on the calculation of 10BASE-T1S. 60.
Okay. Thank you. And in 10BASE-T1S is the same?
10BASE-T1S itself, we calculate 100%, almost.
Almost 100%, because of PLC cycle.
Okay.
Yeah, no care, almost no care for 10BASE-T1S about bus load.
Okay, thank you very much.
Including the header and also the...
And diagnostic traffic?
Diagnostics is not included.
No, not included. Thank you very much.
Okay, I have two questions, just a clarification. So one is you were using burst mode in your evaluation. Is that correct?
I'm sorry?
You're using burst mode for your 10BASE-T1S?
Yeah.
And have you done it if it's only the burst mode was not set to 1 as opposed to, I think you set it to 4? Is
it board?
Well, you set there, so what I saw is that you had the burst mode set to 4. Right, so you're setting four consecutive packets as opposed to just 1.
We use four burst mode.
Right, the burst mode, right. So have you actually investigated just using a single burst mode, because you don't know when a particular frame will actually be enqueued to your MACPHY?
You mean the queue?
Well, okay, let's ignore the question. The second one I had is there's also MACSEC.
MACSEC?
That, for security. I know you didn't do evaluation of it, but that adds extra overhead. And have you looked at the impact of safety or security?
Currently, we don't have any plan to use MACSEC.
Oh, you have no plans?
Yeah.
Okay. No immediate plans or no future plans?
In future.
I have, is the mic on here? Yes. Can I, just one question over this side. Sorry, over here. Yeah, so the presentation seemed to be structured around directly taking CAN-FD messages with a maximum payload of 64 bytes and translating that directly into Ethernet, which is, one could argue that's not the most efficient way to use 10BASE-T1S. So has Toyota considered combining multiple CAN-FD messages, maybe 128 bytes or even longer, and then making that the Ethernet frame, thereby making more efficient use of 10BASE-T1S? I think especially the processing power needed would go down a lot if the payload is increased. Can you make a comment on this?
Yeah, it makes sense. But in this case, we evaluate only for CAN-FD 64 bytes. But Ethernet itself, we are using the up to 15,000 bytes, so that the microcontroller load will be down, will be decreased.
Okay, thank you.
Thank you.
Just-
Hello, Martin Miller, Microchip. Thanks for the presentation, very interesting data. What kind of surprised me was that the SPI versus the OA3 pin measurements were almost in the same ballpark. And so I remember the presentation from Volvo where we also saw quite big latencies. And my question is, could it be that this is more related to the AUTOSAR inner structure and it's not really related to the network?
どうぞ言ってください、それ。
いや、これ考えてないよね。
いや、
Yeah, are there any relationship with the AUTOSAR standardization?
if the chance to adapt AUTOSAR, I will think and promote it.
Yeah, so maybe we should just work on AUTOSAR to make it more performant with the IP stack.
My understanding is that this aberration is not included in the AUTOSAR.
It's without AUTOSAR?
No, without
Okay,
AUTOSAR.
because I thought.
And because
okay.
Linux system.
Okay, then,
Yeah.
then it's not the case. Okay,
だよ
thanks.
ね。Linux。
いや、Linux じゃないです。マイクロコントローラーです。マイクロコントローラーです。
Yes, hello. So it's Giorgio Berguto from Onsemi. So first of all, thank you so much for this presentation. Being one of the guys that contributed a lot to 10BASE-T1S is really rewarding to see this, so it's a honor. My question is related to what Martin just said before. I also note that there is basically the same level of performance of CPU usage between the 3-pin interface and the MAC-PHY. So my thinking is this is probably related to the difference in how the stack really works compared from KNFD to the Ethernet. And you showed you were using TCP there, so you're basically using the protocol stack provided by the operating system. So my question is, instead of just going row layer 2, which is of course an option, how about using UDP instead, which is just a small overhead on top of layer 2, but you will keep retain the benefits of an IP network. Did you evaluate that in your study, or did you plan to also try this?
Now this use UDP.
Okay, but it's using the full protocol stack, yes, of the.
Yes, it's use IP and UDP protocol.
Okay, I understood. Thank you.
Right.
So my point is, you want to evaluate on a smaller operating systems, lightweight stacks that maybe are optimized for UDP, and then also in that case, I would think the latency and the processing time will go down.
You say you must optimize socket adapter and TCP software
Yeah.
more low.
Yeah, I think the protocol stack can be really reduced, especially depending on the platform. If you make this with Linux, then it's high complexity stack. If you use something smaller, I'm sure you will get much better performance. That's just a suggestion.
Thank you.
Thank you.
Yes, I'll make it. Okay, so hello. So I'm Xiaoting from Ampere. Thank you very much for the presentation. I think my question will be kind of continued discussion with the previous question, because I understood that you improved the performance by developing kind of a complex driver in order to make it the execution more lighter. But have you ever considered, for example, the IEEE 1722, the ACF, the standardized solution for the CAN Ethernet tunneling, something like that?
I'm sorry, not yet. Not yet. In future, we will evaluate 1722, but now, not yet.
Not yet, okay.
Not yet tested.
But that could be something promising for you, or you will be willing to consider it, or no, you see some constraint is completely out of the picture? No, for the moment, not the case. Okay,
Not
thank you.
Penfai here from Cititech. Unfortunately or fortunately, my answer already, my question was already asked, so I don't have any. So just ask. Thank you.
Thank you again. Time for a break now, yeah, thank you. So we'll have next conference at 11 about modern E architecture and sleep management. So see you at 11.